We have all heard of the Pythagoras Theorem and perhaps the cosine law for triangles. I just discovered that even my plain old glass of water knows about the Pythagoras Theorem and the cosine law of triangles. Let's see how. So, in some of the previous modules, we've been talking about fluid elements, and we're sort of encapsulating or we're trying to measure the forces being exerted or the pressure being exerted across different faces of such a fluid element. Let's take this idea a little more literally, and this time I'm going to consider a triangular element. And perhaps let's imagine for ourselves something like a sandwich, a triangular sandwich box, which you fill with water, and you take one end of it or one corner of it and tie it to a vertical sort of line, perhaps a pencil or or a string or some kind of a rod that you might have. So let me make this idea a little bit more clear. And then what we're going to do is we're going to study the force balance across the different faces of this triangle and see how fluids know about the Pythagoras theorem. So imagine that you have an axis, and let's say this axis is along the z direction, and we have our regular xy plane. So I'm going to draw a fluid element, or if you want to imagine this a little bit more literally, think of this as a sandwich box, which is triangular in shape. So this is our xy coordinate system. So that's the x-axis and that's the y-axis, whereas the the vertical line that I'm drawing, you can imagine that to be along the z direction, right? So the image that we have in mind is that I have some kind of a pencil to which I have attached the sandwich box, and I'm going to study the torque which is being exerted across different faces of this triangle, assuming that the triangle is in equilibrium, right? So if you know a little bit of mechanics, you know how to calculate moments or torques, and you have a little bit of familiarity with fluids in terms of how it exerts pressure on the walls of the container where you're holding the fluid, then we can work out a very novel way of proving the cosine law for triangles, and as a special case, discover the Pythagoras theorem. And that's the intent of this video. So imagine that you have this line which is in the z direction, and maybe I'll use a dot notation to indicate that maybe the z-axis is pointing above or the plane. And then we have this xy plane where we have this triangular box. Now this triangular box is not entirely planar because we want to fill it with water, right? So I'm going to draw this a little bit more. I'm going to emphasize the depth of this triangle in a way that perhaps makes this idea a little clearer. So we have this kind of a sandwich box, and this sort of enters the third dimension, something like this. And imagine you're filling it up with water. You fill it up with water. Okay. Let's also give some measurable quantities, measurable sort of units to the dimensions of this triangle. So let's say the sides of the triangles have length A, B, and C respectively, right? So this is A, this side is B, and this side is C. And now we're going to fill this box with water, right? Now, if you've seen the video where we talked about how there is a pressure gradient along the vertical column of a glass of water. So let's say the gravitational force is being exerted in the z direction. So we have this, we have a sort of a vertical line, right? That's along the z direction. And let's assume that that's the direction in which gravity acts. And then we have our xy plane where the triangular sandwich box is sitting, which we have filled it up with water. So at the top of this container, which is exposed to the atmosphere, perhaps the pressure is P naught, which is atmospheric pressure. And as you go down, and let's imagine that all the sides have the same height h, as you go down in height, the pressure increases, right? So the pressure as a function of height for the column of water inside this box is P naught plus rho, which is the density of water, times G, the gravitational constant, times h, the total height. Right? So that's at the bottom. But if you go down a distance, say y, or maybe I should use notation z, if you go down a depth z, then the gravitational then the net pressure there would be rho g times c if your depth z below the surface of the water, right? So this is something we might be familiar with from our previous studies. Now the question for us is, let's say we have this kind of a geometrical arrangement, and let's imagine that this triangular box is in equilibrium, which means that all the forces or all the moments or all the torques being exerted about this axis add up to 0. So now let's identify what are the sources of these torques. If this column of water is exerting pressure on the walls of the container, then each of these sides, for instance, this side, and in the diagram that I've drawn here, I'm deliberately ignoring the depth, but imagine that this has this depth h, which we have sort of indicated more clearly in the drawing below. So there is water which will exert a pressure on this particular face of the triangular container, and this pressure is always acting normal to the direction of the face, right? So it'll try to push the face outwards, right? That's by definition how pressure acts. It's normal to the surface on which it's being exerted, which means that the force associated with this pressure will try to rotate this box in this direction. Likewise, we have this particular face, and there'll be pressure being exerted on this side. Now the pressure is being exerted on everywhere along this face, right? So I'm just drawing one representative arrow to indicate the net pressure being exerted, and we're going to make this idea a little bit more quantitative shortly. But for now, let's just see what the scenario is in terms of the different forces being exerted, which we care about, at least for this particular problem. So we have this normal force being exerted on this face, and likewise, we have this third face where a force will be exerted normal to the direction of the face, which will perhaps look like this. So this will exert a torque about the axis. Likewise, this particular force will exert a torque, and this particular force will exert a torque about this axis. And we're assuming that the depth of the container is fairly small. So all of this kind of can be represented approximately like you have this sort of the axis of rotation, and then we have our triangle, something like this, and we can represent this as this particular point about which we can calculate all the different torques. So these are the forces, and we want to calculate the torque about this axis when all of them are pivoted at this particular point. So that's kind of the free body diagram, if you like, for the kind of system that we're considering. Right. So with this idea clear, let's get on in the next part of the video to actually quantifying each of these torques. And then let's impose the condition that the triangular box is in equilibrium, and then work our way out to discovering the cosine law for triangles and therefore the Pythagoras theorem. Hope to catch you soon.